to you more about reliability and how we think about it at Airbyte. We will be saving time at the end of each presentation for questions. So with that being said, I'm going to hand it over to Charles.
All right, thank you. Tonight, we're going to be talking about what it means for an ETL tool to be reliable. But before we jump into that, just to introduce myself a little bit, my name's Charles. I'm a founding engineer at Airbyte, and I lead our engineering team. I've spent my entire tech career moving data in some way, shape, or form. And so in some ways, this presentation is like deeply personal, as much as a presentation about ETL reliability can be deeply personal. But where I sort of like really built a deep appreciation for all of this was at an ad tech company, a big data ad tech company called LiveRamp. And we were doing this like very cool identity resolution product. It was all this cool technology behind that. That was like really our key differentiator. But then in order to power that product, we had to build ingestion and distribution of data at petabyte scale. And that wasn't really a differentiator for us. It was just something we had to do to build the product. And so I came out of that experience thinking like, hey, there've got to be some economies of scale here. Surely we can get to a place where developers at companies like LiveRamp or anywhere else can focus on building product. They can focus on the thing that really differentiates their product and not be thinking so much about having to move data. And so sure enough, that's how I ended up at Airbyte, where our mission is to make data available and actionable to everyone, everywhere. And so you can kind of imagine that like the superhero version of this, like the way I go to sleep at night is like, I'm going to solve ETL for the last time so that nobody else has to. And like probably the reality is like I'm closer to like an ETL mad scientist at this point, but hey, like we're doing all right. And so that's why you have someone like me doing a presentation on what it means for an ETL tool to be reliable. And fundamentally, like what we're going to do today is dig into like all the things you didn't know that you really don't want to know about what it takes to make an ETL tool reliable. But before we dig into that, I want to take a step back and like really think about what it takes to make a good developer tool in general. It doesn't just have to be an ETL tool. And I have a colleague, and he always comes back to this saying, which is a good tool solves a problem better than I believe I could do it myself. And that bar is high. There are a lot of software developers out there, data engineers, data analysts, who all know how to move data or plunge data in some way. And so the user you're working with already knows how to do this. And so how do you actually make it better? Better than they believe they could do it themselves. And I think a good place to start on that is to go back to what is the user expectation here. And I think a really good place to start is a user who's trying to move data. Fundamentally, they're trying to move their data from point A to point B, and when it gets to point B, they want it to be identical, complete, and up to date, and they want it to get there in a timely manner. Sounds easy, right? In fact, I'm here to tell you it's not. And like this whole presentation is going to be totally in like the midwit section of the bell curve right now, where like I think the totally normal expectation to come in with is like the data should just be the same when it moves. And I'm here to tell you there's so many other things that come into it that depending on what the data looks like in the source or what the destination is compatible with, you're going to have to make some set of trade-offs that meet your use case. And so I'm here to just emphatically say, I understand coming from the place of like the data should just be the same, but sometimes the data cannot be the same. And a good ETL product or a good ETL tool is going to be there for you for those cases where the data cannot be the same, and it's going to guide you through that process. And so I really want to use perhaps a sort of odd framework. This is a serenity mantra, but I think it like really gets at the heart of like why this ETL thing is so hard. And it's that I seek the ability to change the things, I seek the ability to accept the things I cannot change, the courage to change the things I can, and the wisdom to know the difference between the two. And fundamentally, building an ETL tool is all about this, because you are in an ecosystem between different technologies that you cannot change. You have to work around the nuances and all the little funny ways that they work, and still provide the user the ability to achieve data reliability. And so what we're going to do next is we're going to walk through 3 examples that I mostly think are kind of fun to sort of like drill into like why is this thing so hard, And from those examples, those case studies, we're going to sort of rebuild what this definition of reliable ETL is. So first, we're going to start with what I call the science of stuck ETL jobs. My guess is everyone in this room has at some point tried to move some data. And I also guarantee that if you've ever tried to move data before, at some point you thought it was stuck. Whether you rolled the tool yourself, use somebody else's tool, use a managed service, it feels like things get stuck. And a really good ETL tool is never going to leave you high and dry. You're never going to be stuck and not know why. But I am here to say that sometimes the data cannot move as fast as we want it to. And I think the easiest example to think about there is just API rate limits. Like most APIs, in some way, shape, or form, are going to give you an API key or some credential. They let you hit their API some number of times within a time period. And if you exceed that, they're going to say, come back later. And so if your job is, I got to pull all this data out of here, you are at the behest of that server allowing you to make another request. This isn't just in APIs. We see the same thing in databases in a slightly different form, where when someone is trying to extract data from a database and like, hey, this feels like it's slow or it's slower than it used to be, one of the most common things you're running into is some sort of workload contention. There's some other big query running on that database, and it's not able to support the extraction of the ETL job and whatever other query is running. And so I want to go back to our Serenity mantra. And the things that we cannot change here is we cannot change that rate limits exist. They simply do. We cannot change the fact that there are other workloads running on databases. But what a good ETL tool can change is it can minimize the footprint it is putting on the API, so it make as few requests as possible to reduce the chance of being limited. Or it can minimize the load that it's putting on the database to reduce the chance that there's some sort of query contention. And it can use all of the primitives that these technologies provide, so batch endpoints, most databases have some sort of dump functionality, to make sure that it is pulling data in the most efficient and low footprint way as possible. But fundamentally, sometimes the data is just not going to move as fast as you want. And what a great ETL tool is going to help you do there is it's going to provide visibility to the user about what is happening so that you're not sitting there saying, why is this tool broken? It should tell you, I am rate limited right now, this is what I'm going to pick back up. And you might say, like, is there more we can do? But like, this information is so powerful to the user because it allows them to make trade-offs. If you are consistently getting rate limited, you might make the choice to replicate your data more frequently so that on each job that you're running, you're moving less data and you are less likely to be rate limited. And so the goal of a great ETL tool is not just to move the data, but it is to provide the user the correct amount of feedback so that they can make the right trade-offs to hit the level of data reliability they're looking for. All right, cool. The next one, the science of compatibility issues. Again, I think I am speaking to a room of people who work in tech, software engineers, data engineers. I'm sorry this slide is a little bit small, but essentially what it's showing you is a compatibility matrix of temporal data types. So that's like timestamp, time, etc. And surely if you've ever worked with data before, you know that this is just a hot mess across the ecosystem. The compatibility across even the most widely used databases is incredibly inconsistent. To take an easy example, down here on the bottom we have Postgres. Postgres supports time with time zone. Turns out SQL Server does not. If you are moving a time with time zone to SQL Server, you're going to have to make a choice about what you're going to do with that data type. But we all knew, right, that temporal data types were a mess. But like, even numeric data types, like there's not particularly consistent compatibility across databases. And so to pick an example here, Postgres supports bit, Oracle does not. And so again, if you have a bit in Postgres, you're going to have to make a choice. But we can get even more esoteric with some of these compatibility issues. This is one that we learned the hard way at Airbyte, which is that Redshift supports, has a limit of 16 megabytes for varchar characters for a single field. And so if you have a text blob that is bigger than 16 megabytes, it's not going to go into that record in Redshift, and you're going to have to make a choice. So going back to this Serenity mantra, the things that we can't change here, we can't change how Redshift works or how any of these other databases work. But what we can change, and what we have the power to do, is in the cases where there is not direct compatibility, we can choose non-lossy conversions where possible. Now going back, remember we were setting that user expectation earlier of the user is looking for identical data. I think I would argue at that point we are not in the realm where the data is identical. It's maybe semantically identical, like going from bit to small int. You still have semantically everything you need there, but the storage footprint is different and it is a different data type. And so really great example of where identical is actually simply impossible. But the other thing that I come back to is sometimes you can't make a non-lossy data type conversion or conversion of any sort of type. And so in that case, you have to drop the piece of data that is not going to work. And you might be thinking, like, you're an ETL tool. Like, you had one job, and you're dropping data? Like, what are you doing? And, like, totally the right response. It's something we say all the time internally at Airbyte. It's like, we have one job, but sometimes, given the factors in the ecosystem, you simply can't move that piece of data. And so the important thing there is, like, what you don't want to do is, like, silently drop the record and move on. Like, that's horrible. But at the same time, you also don't want one bad record to block all of your data. Because then you end up letting one bad record like totally ruin whatever use case you have downstream. And so the key thing, what I think a really reliable, solid ETL tool is going to do, is it's going to give you feedback of, I dropped this record, and this is why. And just to give an example about how we think about this at Airbyte, again, sorry for the folks in the back, but you can imagine sort of like a mock user record. It has like ID, updated at name, and biography. And then we always provide this Airbyte metadata object. And in this case, we're saying we had to make a change to your data because the bio field was too long, the destination could not fit it. And so we have nulled out that field, and we have implanted in the record this piece of information so you know what happened. And that's super powerful. That's incredibly empowering because now the user downstream is able to make a choice based, is informed of this and is able to handle programmatically what they want to do in those situations. And so I would argue that that is like the best place you can be in terms of reliability when you're dealing with these compatibility issues. The last example I want to walk through is pagination. And you might be thinking to yourself, like, pagination, like how, like that's been around forever. Like, how could you possibly mess that up? And the reality is, we're going to focus on just page number pagination, but there's all sorts of crazy pagination gotchas when it comes to ETL. And so let's just pick a super simple example. Let's imagine we have an API, it's returning user records. We're going to assume a super small page size so that we can fit it all on the slide. So we have just page 1 and page 2. And so one key to the property for this API is that it's going to sort the records it returns by updated at. This is a really helpful thing, right? Because if you can imagine you're running ETL jobs on large data sets over time, you don't want to resend all the data every time. You want to know, hey, we got through January 1st last time, so let's pick up from January 1st and keep going. So it's really helpful, you think, to sort by updated at. And so you can imagine maybe like a naive solution here of like, I'm just going to walk through page by page. And so we're going to request that first page. It's going to say, I'm page 1. There are 2 pages out there, and give me these 3 records. And what can happen, so essentially we're still processing page 1. We have not requested page 2 yet. And then someone comes along, and behind the API, some data is updated. And so the record that was previously the 3rd record on the first page with ID 90 went from Charlie to Chaz. Because we're sorting by updated at, it is now the 3rd record on the 2nd page. And so now we're going to fetch page 2, and we're going to get those 3 records. And it's kind of cool, because like we got like the updated version of that record. That's actually kind of nice. We'll talk about duplicates, but won't get sidetracked on that yet. But you can see in this naive solution, we've now skipped the record with ID 10, delta, because it moved from being the first record on page 2 to the 3rd record on page 1 in between us making that request. And so there are a ton of examples of like different weirdness with pagination. This is the easiest one to show. And there's a ton of interesting algorithmic things you can do to mitigate this. But I really want to exemplify here that even the most basic thing of like, don't miss any data can be very hard, and it is very hard to make 100% guarantee if you're paging through an API that is structured this way that you won't miss a record. And this is where things like one of your mitigations here is to maybe make another pass to detect that a record has been missed, And so then you get into the world where you are having duplicates. So I sort of mentioned that earlier. We think about all sorts of ETL jobs in terms of at least once delivery. And the power of that is it helps you avoid missing records, but it means you do get duplicates. And going back again to that user expectation of, I want the data to be identical, that data is not identical, right? Semantically, again, you can dedupe it and you can get it to be semantically identical, but it's not identical. And so going back to our Serenity mantra here, you can't change how APIs do pagination. As much as I would love to be in a world where every API gave you a cursor and there was a guarantee that as you were paging through the API, you were going to get a consistent snapshot of the data, that is just not how most APIs work. But the things that we can do is based on that pagination strategy, we can choose a better or worse algorithm. And so some hallmarks of a really good algorithm there are eventual consistency. It's much better to miss a record on your first attempt replicating, but if you can pick it up on the second one, at least you're not permanently missing it, unlike what I was showing earlier in this sort of like naive implementation where we're going to skip delta and never come back to it. And then the other thing you can do is there are a lot of, and on top of that, there's just a lot of different algorithms you can do based on what the API supports for how you can page through data to minimize the risk of missing a record. And then on top of that, you can also just sort of try to do it again. Like the other naive thing is like, we got unlucky, like let's just do it all again. Can we keep rescanning? And like that's a totally legitimate strategy as well. Obviously a little bit costly. And so like this is where it comes back to the ETL tool has to be the companion here, where it has to set expectations about what is possible and help you make the right trade-off that makes sense for you. Because in that case of, I can just replicate the data over and over and over again, that gets kind of costly. And so that actually more often than not, like just rescanning the whole data set every time, it's actually a terrible solution. But there may be cases where that actually is the right thing. Cool, so we'll walk through 3 cases. Hopefully you're starting to get the idea, like this is actually like a very complicated space. There's a lot of details to get right. This is again, sorry the slide is a little bit small, but this is a sort of simplified representation of how we think about the topology of all the different errors you can run into when doing ETL. And I'm not going to run through all of it, but I've highlighted the ones we talked about in green, and I want to just highlight a couple interesting spots here. Sort of like the top decision point that I think about is the issue going to be a data issue? And so that was what we were referring to before with like the data, you said the data type was a timestamp and it's not a timestamp. Usually in those cases, we go back to what we were saying earlier, you don't want one bad record to block everything. You want the ETL tool to note that, give the feedback to the user, and then proceed. The other side is like all of the issues that happen that are possible just from moving data, like the actual transmission of the data. And I break that down into sort of 3 categories, which are basically like who has to like actually solve the problem when it does arrive. And so the first bucket is transient stuff. And so that would be like being API rate limited. And a really good ETL tool, like I said, is going to notify you that that's what's happening, and it's going to self-heal as soon as the network partition has been removed or the API key is no longer rate limited. But it should never leave the user unsure of what's happening, and it should always self-heal. Then there's all of the things that like a really good tool, whether it's Airbyte or any ETL tool, is going to be working on all of these esoteric problems like pagination and just minimizing the chance that the user runs into any error. And then the final one is error or cases where the user does have to get involved. And I think the easiest use case to think there is like a user is providing an ETL tool with some sort of credential to access, say, like their Facebook marketing data. If those credentials expire for some reason or need to be rotated, like the user has to come back and update them. And so the best thing an ETL tool can do in those cases is give a really specific notification about that, about what is happening, so that the user is able to remediate it quickly. And so this world that we were talking about earlier, going back to the user expectation, getting this identical, complete, up-to-date copy of the data in a timely manner, this tool that just like magically works in the background and I never have to think about it, I think that's an unrealistic expectation of what reliability means for a good ETL tool. That does not mean, however, that we should just like throw up our hands and say, like, I guess reliability is impossible, because it's not. It's just that we have to think about it in a slightly more nuanced way. And so when I think about reliability in the context of ETL tools, I think about, first of all, an ETL tool should be solid enough that you think about it as infrastructure. It does always work, again, with some of the caveats and nuances that we just described, but the tool should feel like it always works. You should be able to trust it as much as you do Terraform or an EC2 instance. Then, the next one is that a great ETL tool is going to strive for that user expectation, the identical, complete, up-to-date data in a timely fashion. And in most cases, it should succeed. It should meet that expectation and make sure that that data gets there in that timely manner. And then on top of that, a reliable ETL tool is going to use all of the strategies I just described to reduce the cases where 2 is not possible. But finally, sometimes 2 is not possible. Sometimes the data cannot be the same. Sometimes it's going to be slower than you want. And a really good ETL tool that has reliability at its core is going to empower its users to achieve data reliability by giving them the right feedback so that they always know what's happening and they can make the right trade-offs for their use case. And so, if this definition of ETL reliability makes sense to you, I encourage you to check out Airbyte, either our cloud version or open source version of our product. And if you are one of the people in this audience who listen to this presentation, you're like, actually all those pagination problems, like those do sound like a lot of fun. Please don't go solve them by yourself. Like, I guarantee you that's not the right way to do it. We are hiring an Airbyte, and you can come here and solve pagination problems all day long. I'd love to have you. But fundamentally, I think with a dev tool like this, there's always going to be an impulse. Can I just build this myself? And hopefully what you're walking away with this presentation with is that there's all of these details here. And a great ETL tool is not going to solve 100% of them for you all of the time. But it is going to have thought about all or most of them, and it is going to guide you through them and give you a great user experience so that you can get to a place where you feel like your data is reliable. That's what I got for today. Thank you.
All right, so before we go over to Sandy, the way we're going to structure this is we'll leave room for 3 questions after each talk. At the end of the evening, we can also make sure people can ask any questions they didn't get answered. So, do we have anyone who wants to be one of the only 3 questions you'll have for Charles before we go to Sandy? On that note, the QR code out front that says join Airbyte, if you're interested in joining us, go scan that after. Otherwise, I think we're good then.
We got a question.
Oh, we got one?
So you were talking about like how the compatibility is showing in different databases. Does Airbyte solve the problem of like the compatibility between like the different data warehouses like Snowflake Databricks? Like Databricks as a delta, Snowflake as iceberg. Snowflake can't trade Unity, Databricks can't trade Snowflake catalog. How do you solve it?
Yeah, so the question is, how do we handle, like there are a lot of databases out there, all with sort of different data types, Snowflake, Redshift, et cetera. Like, how does Airbyte think about handling those cases? The approach that we take is we have a canonical representation internally of all of the data types that we support. And so essentially we build mappings from wherever data is coming from to that canonical data type, and then from that data type to wherever we're sending data to. And so that allows us to have essentially like abstract over the fact that there is such different coverage. But going back to the point I was making earlier, that doesn't mean if you have bit on one side, you're getting bits on the other side. There's going to be a conversion based on that compatibility. Does that answer that question?
Yes. If I may ask follow,
Sure.
like how does the catalogs come in the picture in that case? Because catalog is where the metadata is stored.
Yeah. So the question is how does the catalog of data types come into the picture there? So again, the way Airbyte works is for any time you're pulling data out of any sort of data store, we go through and we detect all of the data that's in there, the schema of the data, and that's going to present, again, in the canonical form I was talking about, how the data is going to be represented in Airbyte. So within the connector, we have already figured out the mapping of bit in Postgres is mapping to whatever in Airbyte. Right?
When you say 64 megabytes, is this like a media, like images, video, or text?
Yeah, so it's 16 megabytes for varchars in Redshift. in this case, this is just bar charts. It's text. This is a really interesting point where you might say like a 16 megabyte bar chart is like a really big bar chart, and like it is. But it's sort of one of the things that when you're building an ETL tool, you don't get the luxury of getting to sort of like judge the data that's going through. Like if you get a 16 megabyte bar chart, you want to do your best to move it. And I would also say, especially with the advent of LLMs, that's getting a lot less crazy. There's a lot of insane text blobs flying around right now. And we absolutely want to enable that use case. So it's more common than you might think.
How fun is it keeping up with like release notes from all these service providers?
Yeah. The question is, how fun is it to keep up with all the release notes of service providers?
And how do we prioritize?
And how do we prioritize it? So the way we think about this at Airbyte is that we categorize connectors at different support levels. And so essentially certified connectors are sort of the cream of the crop. These are the ones that we're making sure always work. And so those are the ones that we get prioritized. And then we rely a lot on the community for, we're really tackling the long tail of connectors, right? And so there are literally millions of APIs out there, right? And so like, we cannot cover them all, and like the only way you make that work is through support from the community. Maybe more information than you were looking for, but like one of the ways we try to have fun with some of this is like, you can use LLMs to try to crawl the internet and be like, oh, we care a lot about Redshift, like let's make sure we get those change logs and dump that into PagerDuty or something if we know a change is coming. So that's some of the solution space that we are working on there. Definitely a hard problem though.
One more round of applause for Charles.
Do you like the clicker?
I don't need the clicker. Thank you.
The microphone is behind you.
While we're at it, let's also do a round of applause for Sandy who's coming on.
There you go. Oh, cool. It shows up. Hang tight, everybody. Thank you for bearing with me as I work out my display settings.
Outside of my laptop.
I think we've got it. We just have to learn how to make it big.
You left it nice.
Yeah, I got it.
Yeah. Hey.
There we go.
Alrighty. Hello, I am Sandy. I'm here to talk to you about data reliability at the boundaries. Extract, load, check, transform. I work as the lead engineer on Dagster, which is an open source data orchestrator that I'll also talk about as part of this talk. One of the reasons that I have opinions on these topics is that before working at Dagster, I spent years as a data engineer, data scientist, machine learning person. I personally fought the battle for data reliability and often lost. The other source of my opinions is my time working at Dagster Labs, the company that builds Dagster, where a lot of my job is talking to organizations that are facing data reliability challenges. We're only 2 slides in, and I've already carelessly thrown around this term, which is data reliability. What do I mean when I say data reliability, and why do I use it instead of a term like data observability or data quality, which you might hear more often? Reliable data is data that you can trust to meet your needs. It's high quality, it's consistent, and it is fresh. Data quality is a huge part of data reliability, but not all high quality data is reliable. So if you book a rental car, that's a van for your whole family to go on a road trip, when you get to the rental car desk, all they have is a 2-seater Porsche. You're getting a high quality product, but is not the one that you need. That rental car company is not reliable. Similarly, if you're given a complete, well-labeled data set, but that data set is unexpectedly missing a crucial column that your data pipeline depends on, then that data set is not reliable. Data reliability is important. When data practitioners are polled about what they care about, data reliability consistently shows up at the top. So for example, this is a chart from DBT's 2024 State of the Analytics report. They asked a bunch of data organizations to rate the importance of different objectives, and a bunch of other polling questions, but that's what I'm focusing on right now. And of all the objectives they were polled about, this objective about increasing trust in data had the highest proportion of responses that selected very important. Here are the results from another survey. In Seattle Data Guy's State of Data Engineering report, among the top 10 issues that data teams face, data quality is right up there at the top. So let's say you care about data reliability. The first question you might ask is, what causes data to be unreliable? And to answer that question, I think we need to move away from surveys and reports and talk about data pipelines. It might be hard to see this, so I'll kind of explain what's going on. But a data pipeline is something that produces data assets from other data assets. When we talk about a data asset, it could be a machine learning model, often a table, a data set, sometimes a report, a file, something that captures some nugget of understanding about the world that's useful in your application or for making decisions inside your business. So data pipelines start with, in this case, what's being shown here is there's someone's beautiful application which has tables. This is kind of the setup that Charles was talking about. Maybe there's a ETL tool that brings that into your data warehouse, and there's a set of transformation steps that take those tables that were brought into the warehouse and then derive sort of more useful data assets from them. So, to make it maybe even more concrete, imagine we have an e-commerce website. Our application database contains tables that track items listed on our site as well as orders for those items. And then we have a data pipeline that relies on that order and item data, and maybe its goal is to produce recommendations that we can use in our application and email marketing. Without any monitoring, data reliability problems can manifest in one of a few different ways. So one is the recommendation pipeline just fails. Maybe someone receives a notification saying that there was an error, and they have to deal with it. Another one is someone notices the recommendations that are produced are nonsense. So maybe it's succeeding, but suddenly people are clicking on stuff less in the emails that we send or in our application. That's bad. That's a thing that we don't want to happen. Third, maybe someone notices a weird problem in a dashboard that was directly built on top of the recommendation pipeline. So maybe we have some statistics that sort of talk about what sort of kinds of items that we're recommending, and someone logs in at 9 a.m. and is like, this looks really weird. These are all very late times to notice this problem. The damage has been done. So users in the app are getting bad results, or a poor decision is being made off of bad data, stakeholders are mad. Ideally, we'd be catching the problem as early as possible at its root. One of the most common root causes of unreliable data is mismatches at the boundaries between systems. So this has been a huge theme of the data engineering incidents that I've faced in my own life, and also comes up repeatedly in conversations that we have about data reliability with Dagster users. Many of us probably have an intuitive sense that problems happen at the boundaries. Boundaries seem scary, but why exactly is this? I think it boils down to a few different reasons. One, which Charles talked about much more eloquently than I will, is that different storage systems have different type systems and constraints. So for example, if you're moving data from an application database, like Postgres, to a data warehouse, like Snowflake, they might just support different column types. Here's my sort of wimpy version of Charles's slide about Postgres timestamp types versus Snowflake timestamp types. First of all, none of them line up correctly, and then second of all, when you look up even deeper, it's even worse than you thought. Good data movement software like Airbyte will make smart choices about how to move this data over and help guide people to this decision, but sometimes there's no 100% correct choice available. You have this redshift problem. Maximum number of bytes, and if you're moving data from some source that has wider text columns, you're going to need to truncate. The conversion is fundamentally lossy, and that will manifest as problems in very unexpected ways if you don't get a handle on it early. Okay, so different types cause problems. Another kind of boundary problem is problems with the boundaries between different teams. So there's often close communication within a team. So the set of people working on software together usually share a set of assumptions about how data is modeled. So for example, they might assume that a null field has a particular meaning, or that a particular column is restricted to a particular set of values. These assumptions are sometimes documented. They're sometimes enforced using database constraints and the like, but just as often they're not. They're sort of tribal lore that you learn through osmosis, and if you're not on the team, you do not learn through not osmosis. When a different team consumes data, they might have a different set of assumptions than the data producers had. And this can cause all sorts of problems when they write pipelines that depend on those different assumptions. Then, last of all, different teams and different systems just have different priorities. So a team that's primarily responsible for developing a web app often isn't going to have analytics use cases as a primary concern. It's not top of mind. Their unit tests are going to focus on the behavior of the web app more than on the data that the web app produces. And even when there's a known bug, it might not be at the top of their priority list to fix it. So, we know there's bad data, but guess what? We know a lot of stuff is bad about our application, and we have to deal with that stuff first. Luckily, data contracts solve all these problems. Okay, just kidding. I don't think that's true. They help, but I don't think we can put all our hopes and dreams on data contracts. I'll explain why. So I'm probably not the first person to introduce you to the idea of data contracts, just to make sure we're on sort of a similar page about terminology. A data contract is an agreement between the producer of data and about the data, the agreement between the producer of data and sometimes the consumer of that data about what the data should look like. It's a commitment to say the data is going to look like this, and you can depend on that. In an ideal world, data contracts do help with a lot of these boundary problems. If you and the team whose data you're consuming can ratify a spec for that data, and they never break that spec without talking to you, you'll never need to deal with unreliable data. However, there are two very hard problems to making this work. The first one is that defining what data reliability looks like ahead of time is very difficult. Until you encounter bad data, you often don't even know what bad data looks like. To have a data contract, you need to know what should go in that contract, and I suspect that's actually like an NP-complete problem at the limit, to sort of work out all the edge cases of what that behavior is supposed to look like. Sometimes what you want is just, this shouldn't change in some undefined way, or things might be bad. The other hard part, of course, is getting data producers to care. So I kind of see the data contracts movement as this great protest movement. It's helped move the Overton window on how much application developers care about the needs of poor data engineers who are downstream of the data they produce, but we've got a long way to go. And ultimately, the job of application developers is to develop applications, not to develop data pipelines. So if data contracts don't solve all our problems, then what does? Well, first of all, nothing solves all our problems. But second of all, I think the average data practitioner should be spending most of their data reliability energy on what is perhaps the most boring, but also the most effective solution, and that is automated data checks. The most realistic way to achieve trustworthy data is with some degree of monitoring and issue detection, so that issues can be addressed before they affect downstream consumers. A check is responsible for determining whether a data asset meets some property, such as whether it contains an expected set of columns, contains no duplicate records, or is sufficiently fresh. So it might check that the data is high quality. This column that's it's supposed to have no values has no values. It might check for consistency. So just make sure the columns have not changed since yesterday, because we rely on these columns. And it could be for freshness. So not all checks are even about the content of the data. It could be about how often the data is updated. So this table is expected to be updated by 9 a.m. every morning. If it hasn't been, that's a problem that we need to do something about. And I'll talk about what I mean by do something about a little bit later. But kind of the magic of checks is that you get to kind of decouple the thing you're checking from this notion of what you do something, of what you do about it. Checks should typically be executed automatically. No one wants to sit in front of their computer executing checks all the time. But this is, can be actually a complex thing. So for batch data, kind of ideally, you're executing your checks immediately after data arrives. And with streaming data, it's often infeasible to execute, every time a new record is there, recheck the entire table to make sure, let's say, that your uniqueness constraint holds. So a more realistic way to execute that kind of check is at a regular cadence. Checks are especially important at the boundaries for all the reasons that we talked about earlier. The number one reason being that problems happen at the boundaries. So you've got some other team's beautiful app, you've got your beautiful data pipeline, but ultimately beauty is in the eye of the beholder. Checking immediately after the data lands allows you to rule out problems in your own data pipeline when diagnosing the root cause of a data reliability issue. An interesting question comes up here. Should you run checks before ingesting the data or after? I think the answer here is actually a little bit context dependent. So if the source system for the data is an application database, it's usually not a great idea to run checks before ingesting the data. A couple of reasons for this. One is that application databases are often not well suited to the kinds of columnar queries that are needed to execute data quality checks. Just not an efficient data storage place to do it. Also, you typically don't want the analytics system placing additional load on the application database. So if you're running heavy data quality checks, you don't want that actually to be slowing down the responses people are getting in that. This brings up this interesting side question that Charles talked a little about, which is what should a data movement tool like Airbyte do when it encounters problematic data? So, for example, unconvertible types, unaddressable mismatches in a set of columns. So ideally, the data movement tool, the ETL tool, brings over data the best it can. And then attaches metadata that explains the choices it had to make. This metadata is not just useful for humans to sort of go and understand what's going on. It's useful for checks. So remember, beauty is in the eye of the beholder. The data pipeline that depends on this data can include checks that read the metadata explaining the problems that were encountered in bringing over the data, and sort of determining whether that is a alertable or blockable or warnable offense. Some problems might matter to some data consumers, but not for others. So that was the case with the boundaries between different storage systems. On the other hand, if the boundary is just between different teams that are sharing the same data warehouse, then running checks before moving data is more feasible. In that case, it would be wasteful to create a copy of the data just to check it. You can just check it in the data warehouse. Of course, there's no point in running an automated check if nobody's going to do anything with the result. But what you do with the result depends a lot on the severity of the problem and sort of what's happening downstream. The most intense thing you can do when a check fails is to halt the pipeline. When you encounter bad or unexpected data, you don't want to let it contaminate downstream assets or dashboards. This is the right option. Sometimes bad data should not be propagated because it's going to ruin the app. Of course, this is not going to help you with data freshness problems. It'll just exacerbate them. The next most intense thing you can do is send an alert. So you interrupt someone's data, tell them that there's a problem. The risk to pay attention to here is that if you cry wolf too often, you get alert fatigue. People start ignoring alerts. So giving alerts severities and routing them to the proper channels is very important when thinking about alerting based on checks. And then last of all, the mellowest thing you can do when a check fails is just to record that failure. Don't tell anyone about it, just be like, okay, we know there was a problem. And the reason that this is useful is if someone runs into a problem downstream and is trying to find out why, then coming across the record of the failure can be a critical piece of information for their debugging workflow. But of course you have to be careful here because some problems actually need to be addressed before they hit some downstream system. There's no single answer here. It really depends on the severity of the issue the check discovers and the downstream consequences of that issue. Okay, so any talk by me would be incomplete without a discussion of how this relates to Dagster. And I think, in addition to me just talking about Dagster, this will help make what I've been talking about here a lot more concrete. So if you're not familiar with Dagster, it is a data orchestrator, in the broadest possible sense of the term. Dagster models and executes data pipelines. But unlike other orchestrators, Dagster takes responsibility not just for executing data pipeline code, but also for the data assets that that code is responsible for producing. So in Dagster, the files, the tables, the reports, the machine learning models produced by a data pipeline are just as important or more important than the actual code that Dagster is executing. The sort of central manifestation of that in Dagster is that when you define a data pipeline in Dagster, you define it in terms of the assets that it produces. And then because checks are so fundamental to data reliability and to sort of understanding these data assets that Dagster manages, Dagster has a first-class notion of an asset check, which I'll talk about in a minute. Also, by the way, Dagster is open source. Everything I'm going to show you here is something you can pip install and run on your laptop. So here's an example data pipeline in Dagster. This is a screen grab from Dagster's UI. I'll sort of talk through it because it might be hard to see. But it's basically a network. It's a graph. And each of the nodes in the graph is an asset. So it starts here with these sort of foreign nodes that represent the data, in the faraway application database that we're pulling in. So here, there's like a table of items and a table of orders. And then the next stage is we have these two tables that are airbyted into the data warehouse. So in this case, Dagster might invoke Airbyte and say, Airbyte, it's time to pull in the latest updates to the items table and the latest updates to the orders table. The next step is to take these tables, which are ideally, as Charles talked about, as identical as possible to the tables in the application database, and then to transform them into a more useful product for machine learning and analysis. So in this pipeline, that transformation is going to happen in dbt. And so someone's going to write some SQL that sort of takes this data, cleans it up, maybe conforms it in some useful way for analysis. And Dagster sort of understands that it's dbt doing that transformation and can invoke dbt to actually do that transformation step. And so each model in dbt gets represented in Dagster as a Dagster data asset. Then finally, we've got an asset here that is produced via Python. So this is, we're producing recommendations. Maybe we're doing inference using some other machine learning model that we have that arguably should be modeled as an asset of its own. But Dagster is, when it's time to update this asset, Dagster will invoke that Python code. And then last of all, there's another asset that is a table of statistics about this recommendation model that's, again, produced via dbt. In Dagster, pipelines are defined in code. So here's the code that generated the pipeline we just saw. I don't expect you to look at this and understand it. The sort of high-level thing is that we're defining assets in 3 different ways. So this is all Python. There's a block of Python that says, here's a set of assets that come from Airbyte. It invokes the Dagster Airbyte integration. There's a block of assets that are defined via dbt, and it invokes the Dagster dbt integration and points to a dbt project. And then last of all, there is just a decorated Python function that creates that Python asset. And so when you run Dagster, you basically point at this file, it executes this Python, figures out what data assets there are and what their dependencies are, and then renders this pipeline. Let's see. Note that in addition to defining what assets exist, we've also defined how to update each of these assets. So for example, to invoke Airbyte, or invoke dbt run, or run some Python code. This means that we can select any arbitrary subset of these assets in Dagster and tell Dagster to run that code to materialize them. When we say materialize them, we mean update them, take this sort of abstract idea of what this should be, this defined in code, and actually execute that code and turn it into a physical table or file or object in some storage system. We can do it manually by clicking that big old button, or we can do it on a schedule, or do it in response to some events happening. And then Dagster handles executing them in the right order. So that is this super short overview of basic orchestration in Dagster. I think maybe this can give us a foundation for understanding how checks fit in. Is there a question?
Yeah, because you cover pipeline, but do you have bottleneck in your pipeline? Because when you use AI, you have a lot of data, so do you have bottleneck? And what's the maximum data the pipeline can take?
So the question was, do you have bottlenecks in your pipeline? You have lots of data, and what's the amount of data the pipeline can take? So ultimately, Dagster says that's someone else's problem. What Dagster does is it takes data transformation steps that are defined in other systems and takes responsibility for coordinating the execution of those data transformation steps. But ultimately, it's other systems that are actually doing the data transformations. So with this DBT step, DBT is going to have the SQL, and then the actual data processing will happen in Snowflake, and Dagster is just there to sync it all up. So once you've got a data asset in Dagster, you can define a check for it. This is what I talked about when I said Dagster has this first-class concept of asset checks. So this is some Python code, if you can't see it. It's a decorated function. It defines an asset check. It uses this decorator to say this is an asset check. It targets a particular asset. So in this case, it's targeting the orders table that we just freshly brought over from our application database. And then the body of this function is code that it can do whatever it wants. But in this case, it creates a Snowflake connection, executes a Snowflake query, and finds a number of rows that don't match a particular criteria. Dagster is extremely unopinionated about the logic for executing the check. So this whole machinery is basically a harness for executing arbitrary check logic that you want to throw in. That makes it very flexible. This means that the check logic can come from other data quality frameworks, like Great Expectations, or SODA, or DBT tests. Most commonly DBT tests in our experience. So if you pull in a DBT project to Dagster and it has DBT tests, those tests will actually be represented as asset checks in Dagster. Very similar to if someone actually wrote Python to define an asset check. So this is just a file that specifies some DBT tests. Another way to build a check is to use some sort of helper method. So this is the way that you construct a freshness check in Dagster. The check will fail if more than 2 hours have passed since the last time that this asset was updated. And it'll just kind of execute in a loop every so often to see if the asset was updated or not. Once you define the checks in Dagster, they show up in the UI. So it might be a little hard to see here, but several of the assets in our pipeline now have this little section at the bottom called checks. So if you're looking at this items asset, you can in addition to seeing the latest time that it was materialized and whether that materialization was a success or a failure, you can see that it has 3 checks and that one of them failed with a warning severity and the other 2 passed. So note that we've chosen to put our checks in 2 places, and those places happen to be at the boundaries. There's 2 boundaries that we're thinking about here. So one is at the root, and these are checks that are happening on data as soon as it's moved over. The other one is at the end. So we want to check our data right before we sort of ship it off to our stakeholders. And we want to orient those checks on stuff that our stakeholders care about. So if they expect data to be fresh, every morning, then we want to have checks like that. So then we'll learn that our stakeholders will be mad at us before our stakeholders are actually mad at us. If we click into one of these assets, we can get more detail about what's going on. And so here's Dagster sort of also can function as a data catalog. This is a page dedicated to one of these assets. It tells us about the results of these checks. If we click in, we can see all of these checks, all the times they're executed. In this case, it looks like the check for our time zones is failing. So you throw back to this earlier slide. You've checked now what? These different options. Basically, Dagster supports all of these options. If you want to block, that's just sort of like a little argument you throw into your Python function. If you set blocking to be true, then Dagster will halt the pipeline if it if it notices a failing check. Use this with caution. The second one is alerting. This is the one exception to where I said everything is open source. Dagster has the ability to send you a Slack message or an email on a failed check, so you can learn about it. And then last of all, tracking. This is just the screen grab that I showed you earlier, where you can understand that a check failed when you go in to debug your asset, even without necessarily getting alerted on or taking more extreme action. So that was the gritty detail on what it looks like to have an orchestrator care about data reliability. And the last thing I want to leave you with, zooming out a bit, is why would you want your orchestrator to care about data reliability? I think the seeds of this were there, but to call it out explicitly, I think there are two main reasons. So one of them is that checks are often part of control flow. Orchestrators are responsible for deciding what to run when. And so first of all, the checks themselves need to be orchestrated. Many organizations have told us that actually their data quality checks are more expensive to execute than their data pipeline. Which, good on you that you're checking your data quality so much. Respect. And the second one is that the checks often determine what else needs to be executed. So, the result of the check will tell you you should block downstream assets from being orchestrated. And the second one is it offers a single place to go to understand pipeline and asset health. So, there's kind of like the dimension of problems that traditional orchestrators track, which is like basically something failed. We're trying to do something and there was a problem. And then there's this separate world of like asset health. Like my data is bad. Like my computation is bad, my data is bad. But ultimately, if you care about data reliability, these aren't separate categories. Like you're just trying to get your data pipeline to run and for that pipeline to create healthy data assets. So the dream of checks and orchestration together is that you end up with this sort of like single view of this sort of like entire health system that you care about. So that is what I had. Quick high-level summary. Number one, data reliability is more than just data quality. One of the main sources of issues, if not the main source of issues, is at the boundaries between systems and teams. Data contracts are cool, but not enough. You gotta check. And checks and orchestration are two peas in a pod. Thank you.
Take some questions.
This is a really cool layer of abstraction, especially when it comes to orchestration. And so I wanted to ask about, like, in development, what was the sort of trade-off that you guys saw between using this level of abstraction versus doing an native, implementing a native solution, and like what sort of latency trade-off would come as a result?
Okay, so the question was, what was the trade-off between implementing this abstraction versus doing a native solution? Yeah. So I'm gonna, if I understand what you're asking, an alternative would have been, instead of having this like very flexible, like check can be everything, actually building a more fully featured data quality system into Dagster. Sort of at the level of abstraction as like create expectations or GPT tests or something like that. So you don't have to leave the system in order to be able to specify checks. Basically, what we've learned as an orchestrator is people want to orchestrate everything. Having come from working on data teams where all I want to do is restrict the set of tools people can use. Like as a generalist tool, you just have to support everything that everyone wants to do, and people have very legitimate reasons for orchestrating the stuff they want to do. So I think our first concern was how can we incorporate all of the amazing stuff people are already doing in data quality rather than sort of force them to learn a new framework. And then if we want to, we can sort of fill in the gaps, build some sort of higher level of abstraction on top of that that is a little bit more specific to Dagster.
Yeah, I'm using asset checks every day, building them right now in my company.
Awesome.
but it's still an experimental feature. So what does that mean? Like you have some experimental feature where you things like automatization, message check. Does that mean that you may give it up, the feature?
Got it. Okay, so the question was, Dagster's experimental features, what does that mean?
Yeah.
Okay, so first, asset checks are actually no longer experimental as of a month ago. So they're a stable part of the Dagster API. They will not go away. The APIs will not be broken until Dagster 2.0, whenever that is, maybe never. The general question, Dagster has a lot of experimental features. Normally an experimental feature doesn't mean, we're planning to give this up entirely, but it means we haven't worked out exactly what the API should look like. We want to let it simmer, get feedback, give ourselves the chance to iterate more before locking into a particular set of Python APIs. We got one more.
For any low latency uses, so you mentioned checks can be quite expensive, therefore I imagine kind of slow sometimes. How is that addressed during time critical low latency use cases? Do you do asynchronous checks or what other kind of alternatives you have?
Yeah, great question. So the question was, if I understand correctly, you have checks in the data pipeline, but what if the data pipeline needs to run really fast and the checks are slower? And so the way Dagster handles this is checks aren't forced to execute synchronously with the data pipeline. They point at assets, but you can actually have them run on separate schedules. And so that's a common pattern we see when someone has very fast-moving data, but very heavy checks, is that maybe they'll update their data every 15 minutes, but they'll check every day because that's kind of the cadence they actually need to learn about problems at. Can I do a couple more? Great.
Does the graph in general support different scheduling? Like you could have a bunch of hourly jobs, but then have daily jobs that will wait for all the hourlies for a certain day to complete before we'll run dailies? Does it have good support for that? I haven't actually.
Got it, yeah. So the question was, does the graph generally support different scheduling? So we looked at this Dagster asset graph. Do we have to run this entire thing daily or hourly to make that choice? The answer is no. So basically you can choose different subsets of the graph to execute at different cadences. And then you can use this thing called auto-materialized policies to, instead of just sort of running on a fixed schedule, actually have when the downstream assets execute be sort of determined by updates to the upstream assets. So to kind of have these different time domains.
There's a ton of great data cataloging and data observability tools that are coming out. You have Monte Carlo, you have Atlan. How are you guys thinking about product strategy with Dagster and the kind of stuff that you're working on? Because you mentioned cataloging, asset checking is kind of the observability stuff that comes with other tools. What are you guys thinking about for kind of big rocks in the next medium term?
Got it. Yeah. So the question was, how is Dagster thinking about product strategy relative to other products out there that are sort of focused on data cataloging or data reliability? The way that we look at it is when you combine orchestration with these sort of capabilities like data reliability or data cataloging, it sort of supercharges it. So you get from a catalog, your catalog becomes a lot more reliable because the system that's producing the data that's being cataloged is tightly integrated with it. From the data reliability perspective, you get this kind of single pane of glass. That's not to say that you should always use Dagster instead of these other tools. There are many settings where sort of you need the sophistication of Monte Carlo, or you can't adopt Dagster as an orchestrator. But we do think that sort of in a set of cases, Dagster makes sense as a data reliability tool or a data catalog.
Just as a follow-up, I guess specifically as it relates to observability and cataloging, it seems that you guys have already made a decision with DBT. You're we're not going to do data modeling, right? But the decision has yet to be made for observability stuff or cataloging, right?
Yeah, so I would say Dagster, we have made the decision to kind of build that kind of functionality and try to be that kind of tool, which is not to say that Dagster is the right fit sort of for every observability use case, but I think we are explicitly trying to be that.
Thank you.
Cool. come up to me after if you have any further questions. Thanks so much.
Sandy hit the nail on the head. We do have another 10 to 15 minutes in this space, so feel free, hang around a little bit longer. You will hear me yelling when it is officially time. We do need everybody out. But thank you all so much for joining. Really appreciate it. Can't wait to see you at the next Data Bytes. And again, thank you, Sandy and Charles. We're really excited about the next one. Talk to you all soon.